For years, we've all been talking about the AI chip, like it's this one magical thing. Well, I'm here to tell you that idea is dead, completely obsolete. We're in a new era now, one of super specialized silicon where different chips are built for totally different kinds of thinking. So let's dive in and break down this evolution piece by piece. All right, and this is going to be our roadmap for today. This lays out the three big eras of AI hardware. Each one had totally different goals, different problems to solve, and, well, a completely different design philosophy. We're going to walk through all three, from the factory, built for raw power, to the super fast courier, and then to the brain.
Okay, so here's the plan. We'll start by busting that one chip myth. Then we'll hit the three big phases: the factory, the courier, and the brain. And we'll finish by looking at how all these pieces are coming together to build something totally new.
All right, so let's just get this straight right out of the gate. This idea of one AI chip to rule them all, it's a total fantasy. I mean, think about it. Building a model from scratch, asking it a question, and then having it, I don't know, book a flight for you, those are three completely different problems. And it turns out each one needs its own unique kind of hardware.
So let's rewind a bit. Back to the beginning, phase one. I like to call this the brute force era. The whole industry had just one obsession: go big. Build the absolute biggest models imaginable. Welcome to the age of the AI factory.
So, what was the goal here? Super simple: maximum training throughput. That's it. The whole challenge was just, how do you feed an entire internet's worth of data to a model with 1 trillion connections and do it as fast as you possibly can? This isn't surgery. It's a demolition job. You don't need a scalpel, you need a sledgehammer. The name of the game was just raw, brute force parallel power.
And this is what that sledgehammer is made of. To pull this off, you needed a few key things. First, insane horsepower for the math. That's what we call flops. Second, you need a massive superhighway for data to keep that beast fed. That's your high bandwidth memory, or HBM. And finally, you have to get thousands of these chips all talking to each other, like instantly. That's where things like NVLink come in. It's the glue that holds the whole factory together. And honestly, this quote just nails it. The chip here is a factory. It's not thinking, it's not reasoning, it's just processing. A fire hose of data comes in, it does the math, and that's it. It just calculates over and over again. Okay, but what happens after the factory is done building the model? The job completely changes. This brings us to phase two, the courier. Now it's not about building the brain. It's about getting answers from that brain to millions of people, and doing it fast, and doing it cheap. And this is where everything gets flipped on its head. The goal isn't raw power anymore. It's all about minimizing latency and cost. Every single millisecond you wait for an answer matters. Every single watt of electricity costs money. This is the world of token economics. Every word the AI generates has a price tag in time and power. I love this analogy because it's so perfect. Training, that's a marathon, a long, grueling slog of endurance. But inference, that's a flat-out sprint. It's all about that explosive speed right from the get-go, just to get you that answer now. And to win that sprint, you need a different kind of runner. You have to change the hardware. So forget those big general-purpose GPUs. Now we're talking about specialized accelerators, ASICs, LPUs. Think of them like custom-built race cars, tuned for one thing. They use super fast memory called SRAM, which is like having what you need right in your pocket instead of running to the library for it. And they use good enough math. They trade a little bit of pinpoint accuracy for a massive gain in speed and efficiency. So there you have it. If the training chip was the factory, this inference chip is a high-speed courier. Its whole reason for being is to deliver that package, that answer, that string of tokens to you as fast and as efficiently as it possibly can. Okay, so we've built the factory, we've got the courier service running, but now things get really interesting. This is phase three, the brain. This is where AI stops just answering our questions and starts acting on its own. It's reasoning, it's planning, it's doing things. And this just changes the entire game. An agent doesn't just spit out text. You give it a big, messy goal, it thinks, it breaks it down into a plan, it decides, okay, for this part, I need to use this tool, maybe call an API or run some code, then it does it, and then it checks its own work. It's this constant loop of thinking, doing, and checking. This new way of working leads to a plot twist that honestly nobody saw coming. The CPU is back. Yeah, that's right. The humble, kind of boring CPU that's been overshadowed by GPUs for years, it's suddenly one of the most important chips in the entire AI stack. It's wild.
So, why? Why is this happening? Well, it's because GPUs and CPUs have totally different superpowers. A GPU is a master of doing one simple thing a million times at once, pure parallel math. But a CPU, it's the master of if this, then that. It's built for making complex decisions, for that branching logic that is the absolute core of how an agent thinks. So just walk through it with me. An agent gets a task. The CPU is like the project manager. It comes up with a plan. Then it delegates. It says, okay, GPU, you handle this creative part. And you, little script, you run this calculation. Once the tools have done their thing, the CPU comes back, checks the work, and decides what to do next. That whole job of coordinating everything, that's classic CPU territory.
And this has led to totally new kinds of hardware built just for this job. A great example is NVIDIA's Verona. It's got powerful CPU cores just for being that project manager. It's got something called hardware-level sandboxing, which is basically a super secure playroom where the AI can run code without breaking anything in the real world. And it has a massive amount of context memory, or KV cache. This is basically the agent's short-term memory, so it can remember what it was doing from one step to the next on a really long project.
So what's the big picture here? Where is all this heading? Well, we're not just making new kinds of chips anymore. We're actually building them into a team, a completely new kind of AI system, or stack. And this table just lays it all out beautifully. You can see the whole journey. We started with training, where it was all about throughput. We were building the brain. Then we moved to inference, focused on latency, using the brain. But look at Agentic AI. The goal now is to orchestrate actions. The metric isn't just speed, it's did the task actually succeed? And the analogy? It's like running a whole company with that brain. It's a whole different ballgame. So if there's one thing you take away from this, it's this. The future isn't about one giant, all-powerful chip. It's about a heterogeneous stack. It's a team of specialists where every chip is perfectly designed for its one specific job. And this is what that dream team looks like. Think of it like a pyramid. At the very foundation, you've got your training powerhouses, the GPUs doing all the heavy lifting. In the middle layer, you've got your inference accelerators, the LPUs, for all the fast talking and quick answers. And right at the top, the peak of the pyramid, you have those new agentic CPUs. They're the executives doing the thinking and telling everyone else what to do. And that brings us to what might be the biggest insight for the next 10 years in AI. The bottleneck isn't intelligence anymore. We've got plenty of that. The real bottleneck is coordination. It's getting all these specialized, brilliant players to work together as a team. So I'll just leave you with this question to chew on. For the first time, we're building the right body, the right hardware, for the incredibly powerful AI brain that we've already created. So what happens when that coordination problem gets solved? What new capabilities get unlocked when that final bottleneck just disappears?